Hello, CPS class. My name is James Biskey. I'm very excited to be in the class with you. My paper presentation is on this paper called Why Does Your Data Leak? Uncovering the Data Leakage in Cloud from Mobile Apps. This was done by Chaoshun Zuo, Zhiqiang Lin, and Yinqian Zhang from Ohio State University. It was presented at IEEE in 2019, and I found this paper incredibly fascinating. I highly recommend you read it and think about it yourself. So, why should we care? Well, unfortunately, you or someone you know has been the victim of a data leak. We all know that, and we all know that as we're trying to be better computer scientists by going through OMSCS, we want to write code that protects against this from happening. And finally, this is actually an interesting case study for many information security concepts that we are learning about in CS 62-63. So let's see what those are. First, here's the sad news. Our data keeps getting leaked. And here's some sad statistics. So Boeing had a $2 billion data breach, persisted for 30 years. Every 39 seconds, a cyber attack occurs. The cost of a data breach is about $4 million to a business on average. It takes a healthcare industry over 100 days to recover from a breach. And just my own personal sad story, my data has been leaked by Equifax, Target, Chase, and at least 11 other companies. It's really sad, according to my Credit Karma report. And then just this week, when I checked Credit Karma, I found out that they got hacked as well. So I'm totally screwed. So it's not a good situation. And one of the reasons for that is that many mobile apps are using a service called Mobile Backend as a Service. And Mobile Backend as a Service is incredible. It handles all of the infrastructure that most mobile developers aren't interested in doing or don't have the capability to do. Things like storage, processing, notification schemes, user management, all kind of that backend stuff. And fortunately, with these cloud services, you can leverage these APIs that will do all these amazing magical things for you in the background, and developers can focus on the UI, the front end, the experience, which is the sexy part that everyone cares about. And so obviously examples of these cloud services are Amazon, Microsoft, Google, and so our security goals are in conflict. One of the main concepts of the last 2 weeks of our class was this conflict between integrity, confidentiality, and availability. And so obviously mobile app and cloud storage security is a conflict between availability. We all want our data to be available when we need it to do something amazing on our phones, and confidentiality. We don't want the wrong people getting into our data, and we don't want them pretending to be us. So how does access control work in the mobile backend as a service? Well, there's these two major concepts, authentication and authorization. So authentication tells the cloud who the user is, and authorization tells the cloud what the user can do. And so there's this diagram on the top right which shows 3 different users. 2 of them are normal users, 1 of them is a developer, and so it goes through these layers of authentication, who you are, authorization, what you can do, and then you get to access the cloud resources and use the app. So normal customers get the app key that has very specific and limited permissions. It can only access the resources that are public to that user in that situation, and the cloud knows where the API call is coming from. On the other hand, app developers get the root key, and so that gives the developer sysadmin permissions. It gives them all backend resources, and developers are supposed to keep it a secret, but do we think that happens all the time? Unfortunately not. So misuse of keys ruins authentication. Unfortunately, cloud providers do not enforce the proper key use much of the time. Looking at you, AWS and Azure. So some app and root keys are actually formatted differently, so that's one good measure. So the developer supposedly can't misuse them on accident. However, if the developers do use the root key for user activity when they're not supposed to, an attacker could use that to gain access to the entire app storage. This would be like an attacker logging in to your machine as admin and getting access to all your files and emails, messages, and being able to wreak havoc in your life. And so from there, an attacker can push phishing messages to steal data from other app users. So here's a table on the bottom, and so I wanted to throw out this concept from the class masquerading. So it's fabricating information that's purported to be from someone, the admin, who is not actually the admin. So this is a comparison of the app keys and the root keys for Azure Storage and Azure Notification Hub. So you can see the account key here and the SAS key. They're completely different formats. They don't look anything alike. So the developer would pretty much have to do this on purpose. For the notifications, there's a listening key, which has the keyword listen, and then there's the access key, which has the keyword full. So again, it's almost the same format, but the developer does kind of have to go out of their way to abuse it. On the other hand, incorrect access ruins authorization. Unfortunately, as well, clouds don't regulate authorization functions in mobile apps as much as they should. So if developers code around the authorization step, if they just say anyone can be authorized, then an attacker again can gain access to the entire database, which is awful. This would be like your Facebook profile having the wrong permissions instead of your spring break photos being hidden away where only your best friends can find them, so your mom can find them. So this would be horrible. So here's an example of the proper authorization. So it says read and write is only if the user ID equals the authorized ID, and that's how it should be. But if you do this incorrectly, a couple ways to do that are read and write are true. So you can always read and write. You don't even have to be a user. And also read and write our authorization is not null. So any user can read and write, not just the authorized user. So both of those are bad. So the authors set out to solve 4 problems. One was, how do they systematically identify these keys that are used by mobile apps? 2, how do they identify the key strings or the values used by the mobile apps? 3, how do they design an obfuscation resilient approach to identify the cloud APIs and key strings? And 4, how do they design a verification approach with 0 data leakage to confirm the existence of data leaks on the cloud? How do they do that while not leaking any data? It's really interesting what they ended up doing. So they created this tool called LeakScope. It's an open source tool built by the authors, available on GitHub. It's dependent on another open source tool called FlowDroid that performs the data flow analysis. So it takes the APK Android files, that targets the cloud APIs and parameters as input, and it generates possible key values using a value set analysis. And I'll talk about what that means in a little bit. But there's 3 components of this tool. There's cloud API identification, string value analysis, and vulnerability identification. And so I'll talk about what those are very shortly. So cloud API identification. How do the authors scan for key API usage? Well, simply looking at the cloud API calls doesn't always work, because the apps can parse and concatenate the keys to thwart reverse engineering and repackaging. So you know how sometimes on the App Store you'll see these awful apps that are just complete clones and ripoffs of an existing app, and it's obvious to everyone, but maybe they just changed the title or they just changed like a skin or something like that. So that's what they're trying to protect against. So they can't do that. So they made a function signature to identify the cloud APIs, and I'll tell you what they did. They ignored the names of things they couldn't count on, like packages, classes, functions, and variables. They made a hash of the strings made from parameter types, local variables, return values, and the signatures of the callees, and also they used the hierarchy of the classes, and they made a hash of those encoded invariants as the API signature. And so they, so on the bottom left is kind of the structure of an app. And so I'll talk a little bit about that in the next slide, but they pretty much focused on all the API calls that they needed to make. They didn't have to decode all the API calls, just a few of them. And they found out what the indexes needed to be for them to find out the values. So here's an example of the callback class. So they might not know what the callback class is called, but they do know where it lies in this hierarchy. It's always going to be com, app name, image helper, or sorry, listener, and callback. And so part 2, string value analysis. how did the authors derive these string values? This is really interesting, actually. So they use a technique called value set analysis, which I didn't know about before this class, but I did a little research to find out what it was for this report. So it analyzes possible values at the binary code level, and then it reveals the string values. So how they used that was that they made a couple of graphs to help them. They made a control flow graph and a data dependence graph. And then they ran the computation forward through using those graphs to compute the key values. So what are those two graphs? Okay, so a control flow graph is pretty much, it maps the paths through the logic that result in the final output, so the key values. I just analyzed this example code snippet that was given in the paper. Basically, you'd be looking for any branches or if statements. So this one's mostly trivial, but I did want to show the branches here for the if statement. So then there's also the dependency graph, data dependency graph. So this maps connections between different pieces of data that result in the final output. And so this is a little more interesting, but it's still pretty linear. So it looks like it tries different possible account name and key values from some numeric seed values, this V1 and V0. And then it goes into the account name and account key. It kind of just appends this correct formatting using the text like default endpoints, protocol, HTTP account name, things like that. So it's in the right format when it goes into the API. And then the third part, how did the authors detect vulnerabilities without stealing the data themselves? How did they detect the weak points without becoming criminals? So they couldn't actually try to steal or steal real data, because that would have been leaking data themselves, and they didn't want to do that because they felt that was not ethical. So to avoid that, they actually cleverly requested non-existent data. So this would be like on a Facebook profile where you've got a, what are the common fields in a Facebook profile? Your name, your birthday, where you live. What's one field that's not on there? What's the name of your pet? And so this would be like asking Facebook, tell me what's the name of this person's pet, and trying it with a key, and then if they got a permission denied, they would know that it's an app key. But if they got a data not found, sorry, we don't know the name of the pet, then they knew it was a root key. And so they could identify these opportunities for leakage with the different keys using this technique. So they use variations of this approach to find key misuses in Azure and AWS, and also permission misconfigurations in Firebase and also AWS. So the numbers are really impressive. They actually crawled the Google Play Store, which had 1.9 million apps. They evaluated 1.6 million apps with their tool, and they discovered 15,000 apps that had data leaks. This is really impressive. I mean, they obviously use a lot of automation, and they use a crawler script to do this. But just the sheer scale of this is actually very impressive. And they pretty much covered all the apps that you can get on an Android operating system. So here are some insights that we got from the paper. So LeakScope apparently works pretty well on these top cloud services. So their resolved string rate was between 77 and 100% on these, so that's pretty amazing. Also, another insight is that Firebase seems to be the most popular for storing these, or at least for doing for inspecting these apps. And AWS seems to be the most vulnerable because they had the highest percent of apps that had detected vulnerabilities. Another insight is that even popular apps can be leaky. This is probably one of the most concerning things that made me really pay attention when I read this, because here's where we start to get vulnerabilities. At the number of downloads, that's 100 million to 500 million. So, those are apps like Snapchat. Those are apps like LinkedIn. So, it's pretty much it's pretty much a sure thing that you have an app that is leaking data, and you really don't want to have that vulnerability on your phone. So it's really important that we pay attention to this phenomenon, and hopefully the cloud providers fix it. And so what kind of data are vulnerable? So we've got examples of the data here. So these are the top 10 vulnerable apps. And so we've got data like user photos, chat history, configurations of the game. Oh, they could mess up your game configuration. That would be horrible. But other things like, your coins. Maybe you've got digital currency. Maybe you got some photos, and then maybe your device information. So if somebody wants to own your device, they could actually do that via a cloud API for a game you play. And so that's kind of a scary thought. So what's kind of an epilogue of this? Well, the authors actually disclosed all the vulnerabilities to the cloud providers, and then in turn those cloud providers notified their app developers. So actually everyone took this really, really well. So Microsoft actually admitted that they had incorrect documentation when they were telling developers to use root keys for some purposes when they really should have had them using app keys. So they said, oops, our bad, use app keys instead. So that was good. Google actually plans to make permission configuration more user-friendly in the next SDK of Firebase. They also added security tests, thank goodness, thank you very much. And now they actually alert developers who use open permissions on their apps. So this is great. So some of the complaints that I had before about these cloud providers not checking that developers were using the right keys, Google is actually addressing some of that. So that's great to see. Amazon was a little bit ahead of both of them. They probably knew they had problems, which maybe were correlated to Amazon's higher percentages of vulnerable apps than the other two. But Amazon actually added permission checks proactively on S3 storage a couple weeks before the authors disclosed it to them. So the timing of that is interesting. And here I will just share a few takeaways that I had. I really enjoyed reading this paper, so it just really got me thinking about how this affects all of our lives as computer scientists and also just as app users, as users of our mobile phones. So first of all, developers can unfortunately be lazy. So here's everybody waiting to use the escalator. I just love that, and it's so true. So yeah, I mean, developers are often under time pressure. They're often juggling multiple tasks, and so you kind of can't blame them. You kind of can blame them for trying to do things efficiently, but maybe you're developing an app and you want to make sure that everything's working, and you don't want to go through the rigmarole of generating an app key every time you want to test. And so maybe you throw in the root key and you say, I'll replace that key later, or it really doesn't matter. So it's really better if you're a cloud provider to design everything so it forces developers to do the right thing, and even transitioning to the next thing, but the next takeaway, it's better if cloud providers share the responsibility. This guy's definitely not being responsible right now, but yeah, I would say that they are actually complicit in data leaks if they are not using common sense security checks and alerts to tell developers when they're doing something wrong. I mean, there's so many things that these cloud providers could have done. I mean, they could have required root keys to come with a username and password. They could have said they can only be accessed from certain IP addresses or called from certain IP addresses. They could have limited the number of times that a root key is used. They could have done so many different things. And it's a little disappointing that they seem to not have thought this through before many data leaks and before these authors released a paper and told them that they had a big problem. My third takeaway was, even if you're using obfuscation, hackers can still get you. It's almost inevitable. So I would implore them to use all the security resources at their disposal. Not only do obfuscation, but use the right keys, use security testing, and use a secure provider. And then you might just convince a hacker that you're not worth the trouble and to move on to maybe an easier target. My fourth takeaway is, so being ethical is a little bit harder, but it's worth it. So the authors, I have great respect for them because they did not take the easy road. They could have just attacked certain apps and then looked for actual data, but that would have been an actual data leak. So they had to be a little more clever to test these keys without exposing user data, but they found a really elegant solution, and I think that they are all the more praiseworthy for doing that. So, good job to all the authors of this paper. And so, what is my fifth takeaway, last takeaway, I promise. I'm actually checking my own apps with this tool. So I got so excited after reading this paper that I actually started setting up LeakScope and FlowDroid, which is the open source tool that it's dependent on, and then the other required tools. And I'm also going to use this setup to run it on the apps that I use on my phone and the apps that my family uses. So we can at least take measures to know what apps are risky and make the conscious effort of whether to use them. And I want to know my vulnerabilities and how to close them. And I also want to be a better citizen as a computer scientist. And so I thought this was a really fascinating paper. I thought it was really relevant to my life and to all of our everyday lives. And this helped me learn some of the concepts in our CPS class, and also just some of the other concepts of analyzing a program and thinking about different ways that you can test it and make it more secure. So in conclusion, thank you so much for listening to this paper presentation, and I hope you enjoyed it. And please let me know if you have any questions. I would be happy to answer them throughout the semester. Thank you.